Hi friends, talking about symmetrical faults. Symmetrical faults are of two types, triple L fault and triple LG fault. Triple L fault, in this case of fault, all the three phase lines are short circuited. These are connected to each other. And in triple LG fault, in this fault also, all the three lines are connected, but apart from their connection, they also get connected to ground. This is the case of line fault. The terminals of generator gets connected to each other, and if all these are connected to each other, and if it is also connected to ground, this will be the case of LLG ground. So in this lecture we will be mainly studying triple LG fault of generator when it was operating under no load condition. Triple LG fault of generator under no load condition. The analysis will be different from when the generator was operating at load condition, under loaded condition. So first we will study triple LG fault under no load condition. No load condition, and the other case will be loaded condition. Fault under no load condition. Let's say we have a star connected three-phase generator. First I will take the case of a star connected, then I will also take delta connected generator. Here we have three-phase short circuit fault. Let's say the generator is given as, the rating of the generator is 1 MVA 11 kilovolt, and its synchronous reactance is given as 0.5 pu. Okay, so under fault condition we have to find out short circuit current and short circuit MVA. Okay, so if this is the rating is given as 1 MVA 11 kilovolt and 0.5 pu, it means this is rating of the three-phase generator. The overall rating of the, if you means combining all three phases, you will have a rating of 1 MVA. We will write the three-phase MVA or MVA three-phase. MVA three-phase, this is given as 1 MVA. Rating of voltage is 11 kilovolt. It means this will be line to line voltage. And the rating in case of three phase, you will be given with line to line voltage. This is 11 kilovolt. Okay, first we are considering the case of a star connection. So in a star connection, line to line voltage and phase voltages are different. So phase voltage will be 11 kilovolt divided by root 3. Okay, and synchronous reactance is given as 0.5 pu. Okay. Let's say this is A phase and this is generated voltage. This is EA. This is the reference for EB, and this is the reference of EC. Here you will have fault current in line A. Here you will have fault current. This is line B. Okay. And since this is a symmetrical fault, the condition to all the phases are identical, so these faults current will be same, and system will still be balanced. If we don't consider any transient, the system will be balanced. So we can calculate current on the basis of balanced system. And this impedance is 0.5 pu, this is also 0.5 pu, and this is 0.5 pu. All the phase impedances are 0.5 pu. So to calculate fault current, what we will do, since the condition to all the phases are identical, we will say that a balanced current will flow. The generation of voltage is balanced, balanced impedances are connected, although these are not external impedance, this is synchronous reactance of the generator only, but the condition is balanced, so a balanced current will flow. Although this is fault current, I will name it as IA, IB and IC. And since these currents are balanced, so the magnitude of these currents will be same. Let's say this is IA, and the phase difference between IA and IB will be, if we draw the phasor diagram, this will be 120 degree, and again IC will lag IB by 120 degree. This is IA, this is IB. Okay. IA will be modulus of its magnitude angle 0, IB will be its magnitude angle minus 120 degree, and IC will be the same magnitude angle plus 120 degree. And if you will take the vector sum from the symmetry also, in the diagram also, if you will add these three vectors, you will get 0. And here also, if you assume, okay, it is very clear that the summation of vector sum of all these three currents will be 0 if these currents are symmetrical. Now if you connect a resistance here or any impedance here and you connect it to ground, basically I am trying to find out potential of this point. Okay, this is connected to ground here, this is also connected to ground, and let's say this current is IN or IG. So if you apply KCL at this point, what will happen? The four currents are coming from this node, so summation of all these four currents will be 0. IA plus IB plus IC plus I ground. And since IA, IB and IC are balanced fault currents, so summation of these three current will be 0, and you will get IG equal to 0. If IG is 0, no current is flowing in this resistance, so the potential drop in this resistance will be 0. This is connected to ground, there is no potential drop across this resistance, so the potential of this neutral point will be, this will be at same potential as the ground. So in the balanced condition, what we can do, we can assume the potential, the neutral at ground potential. Okay, now we have ground here, so to find out the fault current we can apply KVL. You start from ground and you again reach to ground, the loop will be completed. Okay, so let's say this is fault current, where you have positive reference, negative reference. Starting from this ground, here you will have a gain of EA, and EA is nothing but phase voltage. EA will be 11 kilovolt divided by root 3 minus fault current into excess, this will be 0. So fault current will be, or the magnitude of fault current will be magnitude of phase voltage divided by reactance. Okay, and here you are given with the per unit value of phase reactance. So XSPU will be this will be the ohmic value of XS divided by the base impedance. Okay, so we have in the per unit system we have already studied that the actual ohmic value of a resistance or reactance is always same, but for this reactance there may have different PU value that depends upon the base you have chosen. Okay, now this generator is given with an impedance of 0.5 pu. So what will be the base? If a generator is given to you and the reactance of generator is given in pu, so what will be the basis of that pu, or what will be the base voltage and base MVA for that reactance? Obviously the base value will be the rating of, on the basis of rating of generator. Okay, so what I'm saying is there will be some reactance of this generator, there will be some ohmic value and it may have different PU values, but here you are given with 0.5 pu. So this 0.5 pu, this will be on the basis of generator rating. So to calculate actual impedance, we will first find out base impedance, the base impedance of the, on the basis of generator rating. Okay, this is actual impedance of phase, so we will find out base impedance of phase. So what will be the base impedance of phase? That is ZB is the base impedance of per phase. This will be phase voltage divided by phase current, the base value of phase voltage divided by phase current. Now what is phase voltage? Let it be Vp only. And what will be Ip? The phase current. The per phase MVA, phase voltage into phase current. If you consider only one phase voltage and into phase current will give you per phase MVA, per phase MVA or per phase VA. Okay, so what is per phase MVA? The three phase MVA is given as 1 MVA and this will be nothing but rating, MVA rating. Okay, so what will be per phase MVA? 3 phase MVA, that is MVA rating of the machine divided by 3. MVA rating divided by 3, or simply I will write it as rating divided by 3. So what will be base value of phase current, or better to write 3 phase rating or 3 phase MVA. MVA 3 phase divided by 3 into phase voltage. 3 phase MVA divided by 3 will give you single phase MVA, and single phase MVA equal to Vp into Ip. Actually what we are doing, first I am calculating the absolute value of fault current in ampere, then I will calculate the fault current in terms of PU, the PU value of fault current, and we will try to relate the PU value of fault current with the PU value of synchronous reactance. Okay, so this is base value of phase current. So what will be ZB now? The base value of phase impedance, Vp divided by, what is Ip? Ip is MVA 3 phase into 3 Vp, that is 3 Vp square divided by MVA rating of the machine. You will always be given 3 phase MVA rating of the machine. If MVA rating of the machine is given, that will be by default 3 phase rating. Okay, so this is base value of phase impedance. So what will be the actual value of reactance? The actual value of synchronous reactance will be XS. The actual value of phase reactance will be value given in PU into base impedance. The value given in PU is 0.5 into, or let me write it as variable first, the synchronous reactance into P in PU into, here you have divided by base impedance, so here you will have into MVA rating 3 phase MVA divided by 3 Vp square. The ohmic value of phase impedance equal to the PU value of phase impedance into 3 phase rating divided by 3 Vp square. XS PU is equal to, sorry, this is actual value of synchronous reactance. XS actual is equal to XS PU into 3 phase MVA rating divided by, what is 3 Vp square? 3 Vp square is nothing but line to line voltage square. Okay, line to line voltage square will be Vp square divided by VLL is equal to root 3 Vp. So 3 Vp square will be VLL square. So we will write it as VLL square or voltage rating square. And what is this? XS is phase impedance. We always calculate phase impedance. There is no impedance is connected in between line. Impedance is always, we will always have a phase impedance. So actual value of phase impedance is equal to PU value of phase impedance into 3 phase MVA rating divided by line to line voltage square. This we have calculated for a star connected generator, and you please note it down. We will follow the same procedure to calculate the same type of formula in case of delta connection, and then we will compare the two results. So what will be the numerical value here? This is 0.5. Instead of MVA rating, I will prefer to write simply VA. So what is VA rating? 1 MVA. This means we have 10 to power 6. And VLL is 11 kilovolt, means 11 into 11 into 10 to power 3 into 10 to power 3. So okay, this is expression for base impedance per phase base impedance. Okay, value of base impedance per phase, and here you have relation between pu value and ohmic value. So the ohmic value will be xs in ohm. This will be pu value xs pu into base impedance. This is xs pu into base impedance is 3 Vpa square divided by MVA. And what is 3 Vpa square? From here 3 Vpa square will be VLL square. So this is VLL square divided by MVA 3 phase. So actual impedance is the per phase actual impedance is the PU impedance into voltage rating square divided by 3 phase MVA rating. So let us calculate it. This is 0.5, VLL is 11 kVA square, and 3 phase MVA rating is 1 MVA. So kilovolt square will be cancelled with mega, and excess will be 0.5 into 121. This will be 60.5 ohm. So now you have ohmic value of per phase reactance, and fault current is equal to magnitude of voltage divided by reactance. So what is here? We will have fault current as the per phase voltage is 11 kilovolt by 3, 11 kilovolt by root 3 divided by 60. This will give you 104.9 ampere. Okay, and let us also write the value of fault current in terms of variable. Okay, IF is phase voltage divided by per phase impedance. And what is per phase impedance? This is XSPU into VLL square divided by 3 phase MVA. This is nothing but, okay, let it be as it is. So the fault current is 104.9 ampere, and this is in terms of variable. You don't need to remember this, I'm just going to use it. Now if you are interested to find out the PU value of fault current, also this is per phase value of fault current. Phase voltage divided by phase impedance will give you phase value of fault current. And in case of a star, the phase current and the line current are same. So this also gives you the fault current in the line. Now if you are interested to find out the PU value of fault current, we will first, if you are interested to find out PU value, first we will calculate the PU value in the phase only. In most of the cases, first we will calculate the PU value in phase, and then we will find out the relationship between phase and line. Okay, so the fault current, the PU value of fault current will be the actual value of fault current divided by the base current. Per phase value of the PU value of per phase current, so this will be the actual value of phase current divided by value of base current of phase. What is the base value of phase current, per phase current? We just calculated it. Let us calculate again. Phase voltage into phase current will be phase MVA, and phase MVA is nothing but MVA 3 phase divided by 3. So So base value of phase current will be MVA 3 phase divided by 3 into phase voltage. So fault current in PU will be the actual fault current in phase, here you have expression, divided by base current. This is the expression for base current. IF PU will be VP divided by XS PU into VLL square, and this will go into numerator, MVA 3 phase, and then you have to divide with this quantity. This is per phase value of fault current divided by base current. So this is, here you have base current, if you divide it by base current, MVA 3 phase divided by 3 into phase voltage. So this 3 Vp will go into numerator, here you have 3 Vp, 3 phase MVA is cancelled. Here you will have 3 Vp square, 3 Vp square will be equal to VLL square, 3 Vp square, VLL square is cancelled. So what you will get very simple expression for PU value of fault current, and this will be 1 divided by XS PU. You can also calculate numerically. This is the actual value of fault current, and what is the base value of phase current? The base value of phase current will be MVA 3 phase, that means 10 to power 6 divided by 3 into phase voltage is 11 divided by root 3 kilovolt, means 10 to power 3. So you will have 1000 divided by 11 into root 3, 157.45. This is incorrect. 1000 divided by 11 will give you, this itself will give you a quantity less than 100. You cannot get more than 100. This is 52.48. So you have actual value of fault current, you have actual value of per phase fault current, and you have base value of phase current. So the PU value of fault current will be actual value of fault current divided by base value of fault current, or base value of phase current. This is 104.9 divided by 52.48. This is approximately 2 pu, and from here also the fault current will be 1 by what is excess pu, 0.5. This is 2 pu. So although derivation was little bit lengthy, but we got very easy result. The PU value of fault current will be 1 divided by the PU value of synchronous reactance. Now if we do the same exercise for delta connection, we will again get the same result. The PU value of fault current will be 1 divided by the PU value of synchronous reactance. So this is the ease we have. When we represent the quantities in PU value. You don't have to see the star connection, you don't have to see the delta connection, even you don't have to see the line quantity you don't have to see phase quantity. Everywhere the pu value of current will be simply the pu value of voltage divided by pu value of impedance. Let us derive the same thing for delta connection also. Let us, we have the same generator, but now generator is connected in the three windings of generator is connected in delta. Let's say this is first phase, this will be the reactance of winding, and this is the voltage generated in the winding. We have the same generator, means rating is 1 MVA, line to line voltage is 11 kilovolt, and the pu value of per phase synchronous reactance is 0.5. Here also let us consider the three phase fault, and we have to derive, we have to verify whether IF, the pu value of IF is equal to the pu value of fault current is equal to 1 by excess pu. So first let us try to find out the actual value of fault current in the phase. This will be per phase voltage divided by per phase synchronous reactance. This is pu value of per phase synchronous reactance. So what will be per phase voltage? In case of delta connection, line to line voltage equal to per phase voltage. So this will be VLL divided by the phase value of per phase reactance. And how did I write this equation? Fault current equal to phase voltage divided by per phase synchronous reactance. Let's say this is first negative, then positive, then here first negative, then positive, then first negative, then positive. This is the voltage sequence. Now you have three phase fault. So if you start from this point, then you move this way, you will have gain, and you will have here voltage drop in the reactance. Now you move this way, so you will have a closed loop here. Apply KVL here, you will get this relationship. And whatever is the fault current, this fault current is in phase, because in case of delta, line current and phase currents are not equal but hold this relationship. So this is what this current is flowing here, na? Here. Okay, so this is phase value of fault current. Now the phase value of synchronous reactance will be the pu value of synchronous reactance into per phase base impedance. Okay, the phase value of synchronous reactance equal to pu value of synchronous reactance into base value of per phase impedance. And what is base value of per phase impedance? This will be phase voltage divided by phase current. Phase voltage divided by phase current will be per phase MVA, okay, divided by per phase voltage. Per phase voltage into per phase current will give you MVA rating of single phase. This is nothing but Vp square divided by MVA rating of single phase. And this will, what is the MVA rating of single phase? This can be written as MVA rating of three phase. Okay, we will try to represent each quantity in terms of the rating given of the generator. So MVA single phase will be MVA 3 phase divided by 3. So you will have 3 VPS square divided by 3 phase rating. Okay, and in case of delta connection, VP is equal to the phase voltage is equal to line voltage. So per phase value of base impedance will be 3 VLL square divided by 3 phase MVA rating. Okay. So you will get the fault current as, or first the phase value of synchronous reactance XSP will be XSPU into the base value of phase impedance 3 VLL square divided by MVA 3 phase, and fault current will be, this is ohmic value of reactance, so fault current will be VLL divided by XSP. VLL divided by XSP is synchronous reactance, the PU value of synchronous reactance into 3 VLL square, and this will go to denominator, this will go to numerator into MVA. So this is actual value of fault current. This is actual value of fault current in phase or line. Okay, we have moved in this loop and here we have voltage drop. So IF is here. This is per phase value of fault current. This per phase value of fault current. Now if you are interested to find out the PU value of fault current, the PU value of fault current will be the actual value of fault current divided by, or the PU value of fault current in phase will be the actual value of fault current in phase divided by base value of phase current. Everything we are calculating in phase. So what will be the base value of phase current? Again, phase voltage into phase current will give you MVA rating per phase rating. So phase current will be MVA of single phase divided by VP. So this will be MVA of 3 phase divided by, this will be divided by 3, and phase voltage is equal to line voltage. So this is base value of phase current. So you have base value of phase current, and here you have the fault current. So if you will divide these two quantities, you will get the PU value of fault current. Here you have the actual value of fault current VLL into MVA 3 phase divided by XSPU into 3 VLL square divided by the base value of the phase current. So this will be in denominator MVA 3 phase into 3 VLL. So again you will have 3 VLL, you have 3 VLL square, this will be cancelled, MVA 3 phase will be cancelled. So here also you are getting PU value of fault current will be, this is PU value of fault current in phase. This will be 1 by the PU value of per phase synchronous reactance. Now if you are interested to find out the PU value of line current in the PU value of fault current which is flowing in line. If you want to find out the line current, what you will write? The fault current in the line divided by the base value of line current. Okay. You have already calculated for phase currents. So in delta connection, phase current and line currents are not equal, but given by this relationship. So when you will calculate the PU value of line current, in the denominator also you will have √3 into phase quantity, the fault current in phase, divided by the base √3 into the base value of phase current. The fault current will become √3 times into phase current, and the base value will also increase by 3 times. So again 3 times and 3 times will be cancelled. So you will get the fault current in the line, the PU value of the fault current in the line will be equal to the PU value of the fault current in phase. Okay, so we observed that in both type of connections the PU value of fault current will be nothing but 1 upon the PU value of synchronous reactance. Okay, so this thing will be same both in star and delta. There are other quantities like phase values of phase impedance, phase value of fault current, phase value of actual fault current. They may differ. So for better comparison, let us calculate for the same question. Let us calculate each quantity, both for numerical values of each quantity, both for star connection and delta connection. In both the cases, rating is given as 1 MVA, 11 kilovolt and 0.5 pu. In both the cases, we will calculate all the quantities in phase. Okay, so let us first calculate the base value of phase voltage. Here we will have the base value of line voltage is 11 kilovolt. So the base value of phase voltage will be 11 kilovolt divided by √3. Okay, and here what will be the base value of phase voltage? In this case, the line voltage and phase voltages are same. So the base value of phase voltage will be 11 kilovolt only. What will be the base value of phase current? To calculate it, what we will write? We will write the base value of phase voltage into the base value of phase current will give you the base value of single phase MVA. It will give you single phase MVA rating. MVA single phase. So base value of phase current will be, this is 1 MVA, 1 MVA divided by the base value of phase voltage is 11 kilovolt divided by √3. So you will get root 3 divided by 11 kilo ampere. Mega by kilo will give you a unit of kilo. So the base value of phase current is root 3 divided by 11 kilo ampere. Let us calculate here. Here also base value of phase voltage into base value of phase current will be, here we have to take MVA value of single phase. Okay, the rating is MVA value of 3 phase, so you will have to multiply by 3 here. 1 divided by the single phase MVA will be the 3 phase MVA, which is 1 MVA divided by 3. So this will give you 1 upon 11 root 3 kilo ampere. 1 upon 11 root 3 kilo ampere. Okay, in case of delta, again we will write phase voltage into phase current will be single phase MVA, which is nothing but 1 by 3 MVA. So base value of phase current will be 1 by 3 and base value of phase voltage is, so here you will get 1 by 3 into 11 kilo ampere. Just write it separately. The base value of phase current is 1 by 11 into 3 kilo ampere. Now if you compare, the base value of phase voltage is different, the base value of phase currents are also different. Now let us calculate the base value of phase impedance. The base value of phase impedance is nothing but the base value of phase voltage divided by the base value of phase current. This is 11 by root 3 divided by 1 by 11 root 3. This is kilovolt, this is kilo ampere. This will give you 121 ohm. The base value of phase impedance is 121 ohm. And here the base value of phase impedance will be the base value of phase voltage divided by the base value of phase current. This will be 11 kilovolt divided by 1 by 11 into 3. This will give you 3 into 120 ohm, 1 ohm. Okay. The base value of phase impedance will be 3 into 121 ohm. And here you will have the base value of phase impedance as 121 ohm. So in the identical generators, because the rating of generators are identical but connections are different, so the base values will differ. So we have base voltage, base current and base impedance. Now let us calculate actual impedance. The actual impedance will be the per phase, the PU value of phase impedance into the base value of phase impedance. Okay. The PU value is 0.5 into base value is 121. This will give you 60.5 ohm. And here what you will get, and also we will use the same formula. Actual value of phase impedance equal to the pu value of phase impedance into the base value of phase impedance. The actual value of phase impedance, whether we say impedance or reactance, the actual impedance is the pu value of phase impedance into the base value of phase impedance. Okay, here you will get 3 times 181.5. Okay. Z actual is 181.5. And here you have Z actual as 60.5. So the ohmic values, okay, ohmic values of these impedances, this is 60.5, 60.5, 60.5. Okay, and here you have 181.5, 181.5 and 181.5. So in the generators of identical rating, if one is star connected and other is delta connected and ratings are same, in both the generators you have same MVA or KVA rating, same voltage rating and same PU impedances, then the actual impedance in case of delta will be 3 times the actual impedance in case of a star connection. If PU values are same, the actual impedance in delta will be 3 times. Or if actual impedances are same, then the PU value in case of a star will be 3 times. Okay, to make the actual impedance equal, you will divide it by 3, so the PU value will get divided by 3 here. Okay. Now let us calculate the actual value of fault current in phase. Actual value of fault current in phase. This is short circuited. This will be phase voltage divided by phase impedance. So phase voltage is 11 divided by root 3 kilovolt divided by impedance is 60.5. Here the fault current in phase will be this phase voltage is, in this case you have phase voltage is equal to line voltage 11 kilovolt divided by impedance is 181.5. For better comparison, I will write 181 is equal to 3 into 60.5. There you have 60.5. This is 11 divided by root 3 into 60.5 kilo ampere. Okay, so here fault current in phase is 11 divided by root 3 into 60.5, and here you have 3 into 65. Okay, I will write here the fault current in phase is 11 divided by root 3 into 60.5, and in case of delta, the actual value of fault current in phase is 11 kilovolt divided by 3 into 60.5. Now let us find out the PU value of fault current in phase. The PU value of fault current in phase. Okay, we are doing everything for a phase quantity, so if I am not writing anything, it means this is PU value of fault current in phase. So this will be actual value of fault current in phase divided by base value of phase current. actual value is, this is in kilo ampere and this is also in kilo ampere. 11 divided by root 3 into 60.5 divided by the base value of phase current is 1 divided by 11 root 3, and kilo ampere will be cancelled. In case of delta, the PU value of fault current in phase will be the actual fault current in phase divided by the base value of phase current. So the actual value of fault current is this, 11 kilovolt divided by 3 into 60.5 divided by the base value of phase current is 1 divided by 3 into 11. So this 3 and 3 will be cancelled. Here you have 121 divided by 60.5, and here this 11 root 3 will go to the numerator, so this and this will be cancelled. We'll have 121 divided by 60.5. Okay, so next here we will write the PU value of fault current in phase equal to 121 by, this will give you 2 PU, and here also the PU value of fault current in phase, this is 2 PU. So what we can observe here, if generators are identical, in case of a star connection and delta connection, if we compare, the base values may be different. The base values of voltage, current, impedance all are different. The actual value of fault currents are also different. Here actual value is 11 divided by root 3 into 65, while here the actual value of fault current is 3 into 60.5. So actual value may also differ, but if the generators are same, okay, the PU value will be same. The PU value of fault currents are 2 PU in both the cases. Okay, now let us find out the fault current in the line. The fault current, this is the most important quantity. When any fault occurs, we are most interested to find out the fault current in the line. So in case of a star connection, the line currents and phase currents are same. So actual value of fault current, the actual value of fault current in the line will be same as the actual value of fault current in the phase. Here we will write the actual value of fault current in the line is equal to the actual value of fault current in phase. Simply writing the actual value of fault current in phase. Actual value of fault current in line equal to the fault current in phase. And in case of delta connection, the fault current in line will be root 3 times the fault current in phase. This will be root 3 into 11 kilovolt divided by 3 into 65. Okay, here you have now root 3, 11 kilovolt divided by root 3 into 60.5. Okay, if you will compare the phase value of fault current in star and delta, here you have, this is the value of fault current in phase in case of a star, and this is the value of fault current, the phase fault current in case of delta. These two quantities are different, but if you compare the fault current flowing in line, okay, you will find that this is the fault current in line because these two are equal. Now you compare the fault current in line. Here is 11 divided by root 3 into 60.5, and here also 11 divided by root 3 into 60.5. Okay, so this is the reason, or this is the basis we can say that these two generators are identical, because after line whatever is the current is flowing, this will be the behavior of this generator to external circuit or external behavior. Now if you are interested to find out the PU value of fault current, the PU value of fault current which is flowing in line, okay, this will be the actual value of fault current in line divided by the base value of line current. This will be nothing but the actual value of fault current in line will be root 3 into the fault current in phase divided by root 3 into the base value of phase current. Okay, so what you are observing here, both the quantities in numerator and denominator get multiplied with root 3, so again you will get the same result. This is nothing but the PU value of fault current in phase. So the PU value of fault current in line will be equal to the PU value of fault current in phase, so you will again get 2 PU. And in case of a star connection, there is no need to even see what is the PU value of fault current in line, because the currents in line and phase are always same in case of a star. So the PU value of fault current in line, this will be 2 PU only. Okay, so what we are observing here, the actual value of fault current in phases are different, okay, and in line the fault current in line are same, okay, but when it comes to PU, whether it is phase current, the phase fault current in case of a star, or phase fault current in case of delta, or the fault current in line in a star, or the fault current in line of delta connection, these all values are 2 PU only. Okay. So calculation in PU will be easy, because in PU it does not make difference whether you are calculating in case of a star or in case of delta, or you don't even need to bother about the phase quantity and line quantity. Everything in PU will be same. The formula in PU is very simple. Current in PU will be voltage in PU divided by impedance in PU applicable everywhere. And even if you compare the identical generator, the star and delta connection of identical generator, why I am saying these two generators are identical, because in 3-phase fault both generators are supplying the same line current. Okay, so if you have to make identical generators, one in a star connection and the other in delta connection, you will keep the line voltages same in both the cases, but in case of delta connection the actual phase impedance has to be 3 times the actual phase impedance of the star connection. Then in that case the two generators will be identical. You would have also studied that if you want to make star to delta conversion, here the resistances are 1 ohm. In case of delta, resistances are or impedances are gets multiplied by 3. In the same way, here you have a star connected generator and here you have delta connection. So if you will apply a star to delta conversion, each impedance will be multiplied by 3. In this case, in the previous case, what we did, we had a generator, let's say a star connected generator. I'm just making this type of notation for a star connected generator. Then what we did, we wrote this equation: the magnitude of fault current is equal to the magnitude of voltage divided by magnitude of impedance. Okay, the actual voltage is sinusoidal. So what value of in the magnitude, what value we will take? If you are interested to find out the RMS value of fault current, you will take RMS value of voltage divided by modulus of impedance. But actually voltage is sinusoidal, current will also be sinusoidal. So whatever fault current I am calculating here, by using this formula, this fault current is in steady state. The steady state fault current, this formula of calculating fault current is valid. This formula is valid only in a steady state. And the question is, what is the meaning of a steady state? Will there be any transient? Okay, so yes, there will be transient. There will be. Initially the generator was open circuited. Okay, initially these connections are open circuited and the generator was supplying no current. Okay, and suddenly these three got connected to the ground. So suddenly a large current will flow, because impedance is relatively, the synchronous impedance of generator is relatively much smaller than the load. So large amount of current will try to, here you will have, this circuit will have a tendency to flow a large amount of fault current, and this fault current is nothing but the armature current. Okay, so in the next class we will study about the transient. This formula is valid only in the steady state of the faulty condition, but when the fault is initiated, there will be transients. So we will study basically two kinds of transients. Okay, we will study a transient due to DC offset voltage. DC offset voltage or DC transient voltage. And the second transient will be, I'm not sure whether I should say transient or not, but there will be one more factor and which will affect the fault current. Due to DC offset voltage, there will be some effect of DC offset voltage to the actual fault current, and there is one more factor which will have effect on the total fault current. And what should I name that factor? Okay, I don't have a proper name for that factor, but I'm writing here, and in the next lecture I will explain it well. That factor will be due to, I don't have a proper name for that factor, but that factor will be due to large armature reaction. Large armature reaction. When the fault will be initiated, a large armature current will tend to flow through the armature winding. Okay, and due to large armature current in winding, there will be flux which will interact with the rotor flux of the synchronous machine. So there will be large armature reaction. So that factor will be due to large armature reaction, and due to this factor, what will happen? The overall synchronous reactance, and in case of cylindrical rotor machine, this will be direct axis reactance. What we are using here, XS. The value of XS will be changed in the transient period. Okay, this will have three values. This will be called direct axis reactance in subtransient, and there will be one reactance, this will be called in transient. When subtransient will be over, then will come transient, and after transient, the value of, or the total impedance or total reactance offered by the generator will be XS. XS will be greater than XT, means the least value will be subtransient reactance. Okay, and in steady state, the formula for fault current I have derived is this formula, but the reactance offered by generator will be XS only in steady state. Okay, but at the time when the fault will be initiated, the circuit will be in high transient. So in the next lecture, we will study these two factors, and we will try to find out the value of fault current in transient. Why we study the value of fault current in transient? Because we cannot leave the generator in the faulty condition up to the time when the steady state reached, because the fault current is very high. So we cannot leave the generator under faulty condition till the steady state comes. Okay, we have to clear the fault very quickly. So we can say that the fault should be cleared when the fault is in transient. So when fault will be in transient, and this fault will be cleared by circuit breaker. So in that condition, current must be calculated. The fault current must be calculated in transient state only, because the rating of circuit breaker depends upon, it will obviously will depend upon the magnitude of fault current, and magnitude of fault current will be fairly different in a steady state condition and the transient condition. So in the next lecture, I will try to give you reason why the synchronous reactance is different, and the effect of DC offset voltage.